And welcome to my class. Here are my students,
Hey.
and I'm going to try to talk about modern physics today. Alright, first slide. First topic I would like to discuss today is special relativity. Special relativity has two postulates. First is that all laws of physics have the same form in all inertial frames, or frames with a constant velocity, and the other one is the speed of light in a vacuum has the same value, 3 times 10 to the 8 meters per second in all inertial frames, regardless of the velocity of the observer or the velocity of the source. Now, to show this, I have drawn two people. One has a flashlight and the other one is standing on the other side, a distance x from the flashlight. And this flashlight is coming towards that person in a frame S prime, and the origin is in an S frame. And so the speed of light here is c for both observers, and the speed of light here for both observers is going to be c as well, even though in the second case, S double prime, our observer is moving towards the source. Doesn't matter what velocity you have, speed of light is the same. The way that c remains constant in all cases is that there's a flexible idea of time and space. And to exemplify this, I've chosen to use our time dilation example. So in this example, we have a person that has a light source coming out the bottom of a train car, and it hits a detector at the top and bounces back and hits a detector again. So from the at-rest observing frame, it just goes up and down a distance d. And now let's say we have someone standing outside the rail car. As this rail car goes down the tracks a velocity v, that light beam is going to look like it goes up at an angle and comes down at an angle and forms a little triangle. And from Pythagorean identity, we find that this delta t from here, the second case, is equal to this gamma value, delta t prime, which is this original value. So what this equation here says, since gamma is always greater than 1, is that the delta t value is going to be greater than the delta t prime value, or the faster one moves through space, the slower they move through time. Are there any questions?
Yes. Does anything else change to keep c constant?
Yes, actually. Not only does time change to keep c constant, but space is also flexible in order to keep c constant. So an example of that would be if you were moving with a constant velocity to a stationary observer, you would appear to be contracted relative to yourself in order to keep c constant.
Thanks.
First experiment I would like to talk about is the photoelectric effect experiment. The photoelectric effect is when electrons are emitted from a substance due to light striking its surface. This effect was known for a pretty long time, 1899 and 1886, but Einstein was the first one to really explain it in 1905, which earned him a Nobel Prize. So this is the setup of the experiment. Here we have light coming into a tube striking a metal surface, and then that metal surface has electrons that are emitted off of it, and these emitted electrons form a current between these two metal plates. And then this meter over here calculates the current that flows from this electron emission over here, and then this delta V here is varied as you continue the experiment. The findings of the experiment are that or the current, will be 0 until you reach a threshold frequency, and then it will remain at a steady current. It was also found that the current was proportional to light intensity. The actual value of F naught, or the threshold frequency, depended on the certain type of metal you used. The current decreases until it eventually reaches delta V, or its negative V stop. So basically that means that as this current's flowing, it'll reach V stop eventually for certain frequencies. And then V stop is the same for all light intensities at a certain frequency. So no matter how bright the light is, as long as it's like, say, a green light has a 500 nanometer wavelength, no matter how bright or dim it is, it'll have the same V stop value. And so Einstein's reasonings for this was that there were these things called quantized light packets or photons, and their energy was equivalent to h, or the Planck constant, times the frequency of the light. And then more intense light means there's more quanta, therefore a higher frequency means more quanta, meaning higher energy. And then the K max of these electrons is equal to that E minus the work function, which is related to the threshold frequency. This experiment and explanation paved the way for quantum theory and explained a previously unexplained phenomenon. Any questions?
How does the v-stop change if the frequency changes?
V-stop changes as frequency changes because Kmax is related to V-stop, so as the frequencies increase, the V-stop also increases, and then as frequency decreases, V-stop also decreases. But if frequency were to remain the same, then V-stop would remain the same for all light intensities. The next idea I would like to discuss is the Heisenberg uncertainty principle. Can't read it up there, but that is what it says. This stems from originally wave packets, and basically wave packets are just a conglomeration of positions of x and positions of or values of k that create these wave packets that propagate through space towards the right. This propagates, and then this is internalized in a packet. And the principle states that the uncertainty in the momentum times the uncertainty in x is greater than or equal to h bar over 2, and this is a constant. It's equal to h over 2 pi as well. And what it says is if a measurement of position is made with precision delta x and a simultaneous value of momentum delta p, their two uncertainties is greater than h bar over 2. Like I said previously, this comes from the construction of wave packets to formulate a small value of x. And this is just the derivation of that value over there, where delta k, delta x is approximately 1. Their product is equal to 1/2. Delta k equals delta p over h bar, and then you find from that h bar over 2. This was a huge break from the classical thinking of physics, because it was previously thought that if you had enough skill or precision, you could know everything there was to know about the universe. But with this uncertainty principle, that proves that this is just not the case, that there's always some sort of uncertainty in measurement. Are there any questions?
Yeah, what would be an example of a good practical use of this?
So, what I used this for recently, actually, on my final, was to find that there's no way that the electron could actually be in the nucleus, because if you plug in the nucleus's value for delta x and then solve for p, you actually end up getting a velocity that is greater than the speed of light, which is also not possible due to special relativity, which we've already discussed. Next experiment I would like to discuss is both an idea and an experiment, its practical use, is the Compton effect. According to classical physics, the new frequency should depend on time exposure, and this new frequency is of a photon and an electron colliding. But classical wave theory failed to explain the scattering of X-rays from free electrons. And to answer this, Compton found that only angles matter for a change in wavelength and not their time exposure with each other. He also found that some energy goes to the electron and some goes to the new photon. What this means is that the photon that starts the collision with the stationary electron has to have momentum, which is a property of a free particle. This experiment and idea is a leap forward for proof of the photon being wave-like and particle-like, and this also ties back with the photoelectric effect, which is also a way of proving that the photon is both wave-like and particle-like. Are there any questions?
Yeah, so is a photon actually a wave or a particle?
Well, we actually say that it is both. We say that it has particle-like nature and it has wave-like nature. And as we'll see later with the de Broglie wavelength, that actually follows into other cases other than the photon, such as the electron. The next idea that I would like to focus on is Schrodinger's wave equation. What Schrodinger's wave equation is a means of explaining the wave and particle nature in life. It is also a means of expressing energy of a particle and its position in a single equation. And this right here is the whole equation in a one-dimensional case. And it is negative h bar over 2m, that h bar is squared, actually, I didn't say that, with or times the second derivative with respect to x of the wave function plus the potential energy times the wave function equals I, the imaginary number, or the square root of negative 1, times h bar times the derivative of the wave function with respect to time. And here at the bottom we have the time-independent wave equation, which is negative h bar squared over 2m, times the second derivative of the wave function with respect to x, plus the potential energy times the wave function equals E times the wave function. And so with this equation, we're able to understand more deeply the quantum effects of nature. Also, this wave equation is able to give probability if we are able to solve for psi, or the wave equation. And the wave equation, or actually the psi starred, psi starred times psi, or psi squared, integrated over all space is equal to 1. What that means is that if you multiply psi by its conjugate and integrate it over all space, the probability of finding it is 1, or 100%. And so what I have here at the bottom is psi with n equals 1 energy level, n equals 2 energy level, and n equals 3 energy level, as well as on the right-hand side, psi squared of n equals 1, 2, and 3. And that psi squared is equivalent to the probability density of finding the particle in that position. And these are two what we call infinite potential wells. And it's kind of like a particle is trapped in a box. There's no other way it can be anywhere outside of this box. This wave equation is 0 on this side of the box and on that side of the box, so the particle is only found within the box. And if you look at psi squared, you can see that there's 100% possibility of finding it right there in the center, or from the left hand to the right hand side, and then right in the middle is the highest chance of finding it. And then on the n equals 2 energy level, at the first fourth of the box and the last fourth of the box is the highest probability of finding it there. And then same with the third energy level, and it goes all the way up. And the number of energy levels is equivalent to the number of antinodes, or peaks, that these wave equations have within their respective box. Any questions? All right, the next idea I'd like to discuss is Bohr's correspondence principle. And this is an idea that helps link both classical physics and quantum physics into physics. Bohr states that the predictions of classical physics and quantum physics must agree when the quantum effects reach the macroscopic scale, or, in other words, as n approaches infinity in quantum theory, it should be equivalent to classical theory. So we see this as an example when we observe quantum harmonic oscillators, or when a particle goes back and forth. And what I have here is a n equals 10 probability density wave equation. And what my dashed line represents is the actual experimental value of the oscillator or oscillatory function from classical physics. So what we see is that as we increase n, we actually have a trend line or a dashed line that more closely represents what we see in everyday life with classical physics. So, and as I said, as n increases, we get closer to the accepted oscillatory trend. Are there any questions?
Yes. What is n?
N is different things in different equations and principles. In this example here, n represents an energy level. As we'll see in the next slide, or maybe a couple slides after this, when we come back to Bohr, it'll represent the energy level again, but in the atomic scale. So really it's just as we do more and more values for our quantum effects, we should get closer to a classical effect. So as we go from small to big, we should see that it trends towards the big.
Okay.
The next idea I would like to discuss is de Broglie's waves. And how de Broglie came up with these waves is basically he said, if photons can have wave-like and particle-like properties, why can't everything else, including matter? And he postulated that lambda of this wave, or the wavelength, is equal to Planck's constant over the momentum of the particle. And this postulate turned out to be correct and allowed for advancement of quantum physics, which then accepted electrons as both waves and particles and developed into many new facets of quantum theory, such as the wave equation and energy levels from the wave equation. This new idea for matter waves also provided a proof for Bohr's quantized orbits, which didn't previously exist. Bohr just kind of said that the mass of the electron times its velocity and its radius is equal to some integer value of h bar. But now, when we look at an electron as matter waves, we can see from this graph I've drawn that this circular orbit that Bohr was talking about is observed when these waves, or the waves of the electron, interfere constructively, and they would interfere constructively when they are an integer value of lambda equal to 2 pi r, where r is the radius of the atom. And then from our de Broglie equation, we have lambda equals Planck's constant over the momentum of the electron. This is a non-relativistic case. We didn't account for the electron going close to the speed of light, and that's equal to the mass of the electron times velocity. And then solving for MEVR, we find NH over 2 pi equals MEVR, and H over 2 pi is just H bar. And like I said, this is an idea that was a breakthrough in the advancement of quantum theory and quantum thought, and it provided new insights to particle-wave duality, such as the electron being both a particle and a wave. Are there any questions?
Yeah, so if I were to throw a baseball or hit a golf ball, would that create a wave?
You asked because that would have a mass and a velocity. Yes, it would have a wave, but this Planck constant up here is so small that it would actually lead to a wavelength that is inconceivably small, and we would not be able to observe it with the naked eye. And we've actually never been able to observe macroscopic wave-like properties. So the next experiment I would like to discuss is J.J. Thomson's experiment. In this experiment, he proved that the electron exists, which was a previously unknown particle. So how this experiment works is an electron is fired in through this little tube here, and it starts here at the left and goes to the right, and it passes through these two parallel plates that has a plus V on the top plate and a negative V voltage on the bottom plate, and they're separated by a distance d, which generates an electric field that the electron feels, and it'll move accordingly. And if it passes through here, it will go up to a position D if the electric field is on. And then there's also a magnetic field that is produced pointing into the page. And when this magnetic field and this electric field are equated in such a way that the particle goes in a straight line ending up in F, we are able to equate them and find that the charge on the particle divided by its mass is equal to the voltage on the plates times the angle of this movement here of the particle relative to F, divided by the magnetic field squared times the length of the plate times the distance between them. And so what this was, or how this is important, is it proved the existence of a new particle with mass that was much less than the proton, because this E over ME is far smaller than the value for the proton, which is a heavier particle. Are there any questions?
Yes. How would the B field be created?
This B field would be created, I think, in his own experiment. He used a magnet, but from previous knowledge, I know that you could create a similar B field with what's called a solenoid, which is basically just a like a cylinder of wire that's coiled around that cylinder, and then a current is ran through that coil, and it generates a B field depending on how you orient the coil, either into or out of the page. The next experiment I would like to discuss is the Millikan oil drop experiment. And this oil drop experiment was another step forward in particle nature because it found the elemental charge, kinda. And so how Millikan set up this experiment was he had two parallel plates similar to J.J. Thomson, and he had oil droplets sprinkled into the middle, and then he would try to get these oil droplets to float by changing the voltage on the battery that he had, and he had a switch in the current that he would flip on and off in order to make the particle either float, or not particle, the oil droplet either float or fall. And field is turned on and off to find the velocity. Yeah, because this oil droplet is going to feel a drag force as it goes towards the ground or succumbs to gravity. And there's a lot of intricate math involving the viscosity of air and the density of oil and the electric field and the mass of the oil droplet. But what we end up finding is that the elemental charge is somewhere on the order of 1.6 times 10 to the negative 19 coulombs. And this was also kind of a situation where Millikan really made this experiment to fit the theory, because he kind of had an idea of what it was going to be from previous experiments and previous theories, but he really was trying to finagle his way to get what he wanted. Are there any questions?
Yeah, what do you mean by kind of found the elemental charge?
Well, he kind of found the elemental charge because it was more, he found a range of values that it could be. He said it could be somewhere between like 2 times 10 to the negative 16 to 2 times 10 to the negative 20. He found really a decent range because, as you can see from the setup of this experiment, it's not really made for precise values. It's kind of really just eyeballing it. I mean, he had to take a stopwatch and measure how fast the oil droplet fell to the ground before the electric field was turned back on, but he got pretty close, so that's why we remember him and why we're talking about him right now. Final topic and experiment I would like to talk about for this is the Frank-Hertz experiment, which was a direct proof of the energy quantization of atoms. So how this experiment was set up was we have a filament over here, that is hooked up to a 6-volt battery, and it shoots off negatively charged electrons with an energy corresponding to its accelerating voltage from a battery that is alternating in its voltage from 0 to 40. And then it interacts with these mercury gas clouds, and then these electrons will then pass through these gas clouds and hit this collector all the way on the right, and those electrons hitting that collector will form a current that then flows all the way down to this retarding voltage of 1.5. So the electrons are given energy. The hydrogen gas, or not hydrogen, the mercury gas, was found to only accept discrete levels of energy, which is seen from this graph of experimental results up at the top, where the current from that was examined here against its accelerating voltage that was varied here. And so as we crank up the accelerating voltage and give these electrons more energy, we see that at certain points it'll dip down. The current will dip down, and those are the points where the mercury gas is actually accepting these energy levels of the electrons and emitting photons and light. So, as I said, this is a direct proof of the energy quantization from atoms, which was previously theorized but never really proven, but we have real-life data showing it here. Are there any questions?
No.
Awesome. Hold on. Thank you for being here, everyone.
Yay.